All right. Good evening, everyone. Hi, and thank you for joining us for the first IQC Fireside Chat. My name's John Donohue. I'm the Scientific Outreach Manager at the Institute for Quantum Computing. So the IQC is a multidisciplinary research institute at the University of Waterloo where we're studying the potential and the development of quantum information science. We have researchers working on the cutting edge of physics, chemistry, mathematics, computer science, and engineering. And during these fireside chats, you hope to learn more about the people who are discovering just how the quantum world works. Now, before we get started, I have a few housekeeping notes. So during the fireside chat, we'll be discussing life, careers, research, and science. So first, we'll be going through some prepared questions. Afterwards, we're going to open it up to questions from you. So please ask us questions in the Q&A box. You should see that over on probably the right-hand side. Enter any questions there, and we'll try to get through as many as we can before the end. Just a quick safety note, the chat is open, the chat is public, it's not policed or monitored. So if anyone's posting links in there, be careful with what you click on. Today, our special guest is Professor Ray Laflamme. Ray is a professor at the Institute for Quantum Computing and the Department of Physics and Astronomy at the University of Waterloo, as well as an associate researcher at the Perimeter Institute for Theoretical Physics. Ray is from Quebec City and earned his PhD from Cambridge University under the supervision of Stephen Hawking. He was a staff researcher at Los Alamos National Laboratory until 2001, when he moved to Waterloo to become the founding director of the Institute for Quantum Computing. Ray's research portfolio is incredibly broad, but he's perhaps best known for his work on quantum error correction, quantum information processing using nuclear magnetic resonance systems, and laying out the initial framework for quantum computing with linear optics and photonics. Ray has received many honors over his career, including most recently being inducted as an Officer of the Order of Canada in 2018. He's the Canada Research Chair in Quantum Information, the Chief Strategy Officer and co-founder of Universal Quantum Devices, a local startup, and he's an avid outdoorsman. Thank you very much for joining us tonight, Ray, around this lovely fire.
Thank you very much. Great pleasure to be here.
So this fire is actually a picture that you sent us. So why don't you tell us a bit about what this fire is and where we're sitting?
Well, from time to time, I get some crazy project that happens and some kind of funny coincidence of somebody says something and suddenly a spark comes in and I get involved in something. So a year and a half ago, a friend of mine came to me and he says, Ray, we've talked about going canoeing together. Why don't we start with the basics and build a canoe? So I look at him when they're big guys and say, well, I've never done this. I can go on YouTube and trying to find something. Turns out that there's somebody between Waterloo and Hamilton, a company called Carlisle Canoe. And you tell them you want to build a canoe and they help you and they guide you in the process of doing this. You do most of the work. But when you get to the tough part, they kind of give you little hints here and there how to do this. So my friend Michael Duchesne and I kind of got together and we built each a canoe. And then we had to go, as an experimentalist would do, go and try if it does float or not. And so the experiment was fruitful. The canoe did float. So that was a trip we did in Algonquin Park. We went for 5 or 6 days and we canoed around. And one beautiful evening, we made this fire. And I thought it was appropriate for this fireside chat.
Absolutely. I think we have a picture of that canoe. We can bring that up on the side. But so you've spent some time building canoes. You've spent some time building research labs. Which one's harder?
Canoe goes a little faster. And with canoes, you know exactly which piece goes where. And you have somebody who tells you, you have to do it this way. And they guide you. Building an institute is a bit different. Like the cards are totally blank when you start. And there's not one way of doing this. There's many ways. And depending on an institute for what it is, then the formula varies from one to the other. I've not been trained to build a canoe and not been trained to start an institute either. But definitely the institute takes a lot more time, a lot more patience, and a lot more people around to kind of put it together. So canoe, I was with a friend doing this, but you can probably do it as a one-man job or one-person job. With an institute, there's no way you can do this. So many people put their hands in the dough for the institute.
Mm-hmm. So this was a project, I believe, if I remember correctly, from about a year or so ago. What's been keeping you busy in that? Have you had any new projects since we've kind of been isolated for the last little while?
Yes, the world has changed quite a lot in the last year. In fact, the last 6 months, the COVID pandemic has changed the way we look at the world and the way we kind of behave in day to day. Must admit, the first 2 weeks of the pandemic, I thought for me, and so my kids are grown up, so I don't have to worry about them going to school or not, and they have jobs and they could work at home. My wife had just kind of taken retirement, so we didn't have any kind of deadline, which were very, very specific. I thought the first 2 weeks were absolutely fantastic. Things were very quiet in town. There was nobody kind of going around. Time for reading, catching up on all the reading that I wanted to do. But then after 2 or 3 weeks, things started to become a little bit more hectic. People started to learn about Zoom and all these kind of conference things. And then the day-to-day routine came back. So I got more of a busy. So I started a project with one of my students, Cheyenne Majidi, writing a book on quantum computing, on implementation. And it's one of these things where before starting, you say, okay, yeah, we can probably do this in a couple of months. We're still working on it. We have some reasonable draft right now, but it's a lot of work. And then I'll be teaching next fall. So one of the things that I started to think is, how will I teach? Usually I go to Blackboard. I like to do Blackboard lecturing because it slows down the pace at which I talk. And then I can explain things in more detail with a Blackboard. So I was not too keen on teaching with PowerPoints or kind of view graphs. So one of my colleagues at IQC built one of these things called a light board, and he gave the plans to other people. So I said, oh, I'm going to try this. I'm relatively good at doing carpentry with a chainsaw, but the really refined thing I've learned doing with the canoe. So I said, maybe I can do this. So I built this thing, and you can see on your left kind of one of the trial of seeing how it works, and I think it'll be okay to teach. So I hope the students will give me feedback about how this teaching is going and kind of how can I improve, because this is a really new things for all of us.
So where is that light board right now?
So it is in my basement. So a few years ago, we moved, my kids left home. So we moved from a big house to a small one, thinking that we didn't need any more space. So the slide board thing is, so the piece of glass is 5 feet by 3 feet, and it stands. So it's about 6 feet high. And we have only 2 spare bedrooms in the new house. But my daughter is coming here from time to time, and then my son, who lives in New York, is going to come and visit and be in quarantine here. So need a little bit more space. So I decided to put in the basement, and I could barely fit it next to this green beams and the sink on the right. And I have to squeeze around to kind of get on the other side, but it works. So
just hoping you never need to use that sink ever again.
No, it's still usable. It's all in there.
Amazing. And I guess the people who are paying attention might have seen we quickly flip past this picture that you sent us as well. So first off, these look delicious, but can you tell me what we're looking at exactly here?
So on the right, it's a wood fire oven. So you mentioned what keeps me busy during lockdown, or in general, what kind of things I like to do. So my prime thing that I do in my life is working on quantum computers and try to make them a reality, try to control quantum system and do things. But you can do this. You cannot do this 24 hours a day for 25 years in a row. So from time to time, I need to get distracted on doing things. And as I mentioned before, I like to get some projects which are faster than building a quantum computer. So the wood fire oven was one of them. So I like cooking. We have a little piece of property between Durham and Owen Sound in north of Waterloo. And so I decided to build a wood fire oven. So you can see a little bit of a black piece in the middle. So that's the hole for where the oven is. And on the left, you see bagels we've made a few weeks ago and the fire at the back. And not only they look good, they were good also to eat. I can
Yeah.
tell you that.
Oh, haven't had a wood fire bagel in a few years, and they look amazing. They look amazing.
So we'll get rid of this pandemic, and then we can have a party with bagels.
Amazing, amazing. All right, so we're going to move on to talking a bit more about careers. So for those people who are joining us who are not in the quantum field, can you give them like the quick 60-second breakdown of what quantum is or what you think about when you think of quantum?
It's funny you say the 60 seconds because I quite often ask my students, can you say what you do? You have 5 minutes. And they've never made it in the 5 minutes. If you say 5 minutes, it'll take 7 or 10. And if I give them 10, it'll be 12 or 15. So your 60 second, I'm not sure I'll get in there. But we all kind of observe and look at a piece of the world around us. And me as a physicist, I think about the physical world and how is it controlled and how does it behave. And if you go outside and you drive your car or kind of use a bicycle or walking, you use the classical laws of physics, the one we've inherited from Newton and Galileo and Newton, which tells us kind of how it gives us a picture of the world and some set of tools to predict how the world behaves in the future. So if we know where things are right now, the laws of Newton tells us what will they be in the future. And at the end of the 19th century, Maxwell did the same thing, not for kind of particles, but for electricity and magnetism. So we have a set of laws called the classical laws of physics, which describe incredibly well the world around us. But not everywhere. When we look at very small systems, atoms, molecules, we realize that the laws of Newton, the laws of Maxwell's break down, and we cannot understand some experiments, and some of them are relatively simple. The laws of Maxwell's cannot tell us what is the radiation spectrum of the element in your oven. So you know that you turn it on and it becomes red, and you can say, can you predict which color it will have? The laws of Maxwell's don't. So, and then there's a new theories that come in, which is called quantum mechanics, which describe how atoms, molecules, electrons work. And they explain why the element in the oven kind of is red.
Mm-hmm. That was almost 60 seconds. That was kind of in there.
Okay, I tried.
No, it was pretty close. It was an A+ effort. I think it was maybe 75 seconds. We'll count it. We'll round.
I was waiting for you to tell me stop.
I would never dare. So quantum physics it's an interesting field for sure. It's a field that I also love myself, obviously. Did you have like an aha moment at any time when you like realized while you were studying in high school and university where you realized that you wanted to be in physics and specifically in quantum physics?
So the quantum physics part came a little bit later, but that I wanted to become a physicist came in when I was I grew up in Quebec City. So I went to Cégep, which is like the 2 years before university, between what we call secondary school, grade 5, and university. There's a 2-year period. And so I went to Cégep. And I must admit, on my first year of Cégep, I had no clue what I really wanted to do. I was good at math, good at physics, things intellectual I was good at. I love mathematical problems were for me like puzzles, like just kind of try to find and solve them. And so I had quite a lot of fun at doing this, but thinking about the career, kind of no clue. And when you apply to university, you don't apply at the end of your Cégep, but kind of pretty much halfway through because it's the fall before. So I applied to do something called actuarial science because I was good at math and so, oh yeah, that kind of might work. But in winter, and that was the winter 79, winter 78, I had a prof at Cégep who taught special relativity of Einstein for kind of Cégep students. And
okay.
So I I knew there was a bit of math there. I liked physics. So I said, okay, I'll go and learn about this. And I got totally mesmerized by that field. And suddenly we were doing some mathematics, which was describing that time is not flowing the same way for people who are in different reference frame. And I had zero intuition of that this could be possible, and that this really was happening. Like, I could go through the math. And then the prof kind of explained all the math parts, and then he started to explain experiments where these things would be seen. And there's one where they look at cosmic rays, and they look at the amount of who are decaying at a certain rate. They look at the amount of cosmic rays at the top of a mountain, and they go at the bottom of the mountain and look at how many are left. And if you use Newton's theory, you'd get totally the wrong answer. And if you use Einstein's theory of special relativity, you get bang on. And to me, that was a revelation in many ways. First of them is that really you can use mathematics to understand the world around you, and that the world around you is very different than what your first intuition is. That you get trained, you get intuition about the things you can touch, but the world around you might be different than things that you can touch when you grow up. Mm-hmm. For example, to see the special relativistic effect, you need to go near the speed of light. And we don't go near the speed of light, so we don't see these effects. But in part, cosmic rays do. And then if you find the right experiments, you'll see these kind of pieces. And to me, this was a revelation that the world is very different than the one that I had conceived. And I wanted to learn more about this world. I wanted to know how it worked. So I decided to switch from this actual science and to go to physics.
I mean, I think a lot of people can relate to that. I mean, I know from my personal experience, I did not know I wanted to be a physicist. I just kind of accidented my way into it and just fell in love with it as I went. So I hear that from a lot of people. It's kind of a common way of getting into physics. Yeah. But I guess you've made a few jumps. So not only from actuarial science to physics, you initially did a lot of studies of quantum gravity. If I understand correctly, that's most of what your PhD was on. And from there, you went into quantum computing. That already is a big jump. The jump that kind of astounds me as an experimental physicist is that you jumped from doing like very hardcore theory to like building a nuclear magnesitance like experimental lab. So what drove you to make those leaps, especially the leap from theory to experiment, and what resources and like what did you need to make that happen?
I think that the most important element is curiosity, for a reason that I don't understand. I am incredibly curious. Like when I see things around me and I look at phenomena around, I want to know. I want to know something. And I don't understand what kind of drives me to one thing or not. And maybe physics was the piece where I can be curious about it, but there's a way to understand it. And I can think about other piece in society where it's much harder to understand. How you lead people, how you govern a country is something which to me is kind of puzzling, and I don't know how prime ministers do it so that the country moves forward. But in physics, I can understand that piece. I can relate to this. So this is the main part that kind of started me in my path of why I wanted to understand quantum gravity in the beginning of the universe. And although I did some astrophysics also at some point, but I was always interested in the piece of quantum gravity of what happens if, well, we know about the Big Bang, and the Big Bang tells us that the universe is expanding. If the universe is expanding today, it means that yesterday it was smaller. And the day before, it was even smaller. And then the day before, it was even smaller. And then at some point, it must be so small that it becomes a point where we call the Big Bang. But before it comes to that point, quantum effects must be important. And so we should, if quantum mechanics is the right theory that we can describe the whole universe as, it must be important in the early universe. So I tried to understand this. And so the work that I did is something called quantum cosmology, assigning a wave function to the universe and try to make sense of it. And so I was trying to understand what does that mean to have a wave function for a universe. In quantum mechanics, when we have a wave function, we interpret it that way. So if you have a two-level system, like in quantum information, a qubit, well, you repeat the experiments many times, and then the coefficient in front of the zero gives you the probability of being in zero, and you do the experiment again, and then you look at how many times you get one, and then you get the probability of get one. So that's how we interpret the wave function in quantum mechanics in the laboratory. But for the universe, we have one shot at it. We cannot repeat the experiment, or at least I don't know how to repeat the experiment. So how do you
take a while, for sure.
Exactly, and I might not be there for the next round, or I can be reincarnated in some different ways. I'm not sure I will remember that question. So how do you interpret that wave function? And there was somebody at Los Alamos National Lab who was working on ideas similar to this, called decoherence, saying how do you use a wave function and you turn it into classical probability predictions. So I went to work with him. His name is Wojciech Zurek. And so I went to work with Wojciech. And while I was there, one day there was a conference in Santa Fe. And he said to me, Ray, there's a really neat conference on the physics of information, and you should go. And he was one of the organizers, so he might have been a little biased. But so I said, I have too many things to do. I want to finish different things. So he says, it's just half an hour from Los Alamos, so you should go. So I decided to go. And at that conference, there was a person whose name is Umesh Vezarani, computer scientist from Berkeley, who gave a talk and he started this talk by saying, I'm not going to talk about my work because I've not done anything interesting in the last year or two. And anybody who knows Umesh, he always has interesting things to talk about anytime. So that surprised everybody. He says, I'm going to talk about an algorithm from somebody called Peter Shor of how to factor numbers which are part of prime using a quantum computer. So I went, there was a buzz at the conference that this was really interesting and important. So I went back after the conference and I said, oh, these quantum computers, decoherence, the stuff I was doing with my mentor in Los Alamos, Wojciech Zurek, is going to be the main challenge for these quantum computers. Decoherence will kill any advantage that they have. So I started to work on a small model and try to show that indeed they would be useless. And I got scooped. I got scooped by somebody else who turned out to, I had done a postdoc in Vancouver with somebody called Bill Unruh, who also did work on decoherence. So he knew about all of this. He was at the conference in Santa Fe. So yeah, we had exactly the same idea. But now that's where kind of sometimes sociology plays a role in the science that you do. Bill is a really clever guy, very nice, very smart, and loves to argue. You tell him white, he will argue for black. You tell him black, he will argue for white. As a postdoc of him, that was very painful, of always having to argue. Although, looking back, it was a really good training. It taught me that if I have an idea and I'm with scientists, I have to debate it. And I have to, and when you debate it, you find what are the assumptions, you see where the pitfalls are, you know where the limitation of your ideas. So it was a painful, but a fantastic training. So I just used his idea. I started to take his paper and try to demolish it, to try to call at it, and there was a few holes here and there. And while I was doing this, I stumbled into something called quantum error correction. which is a method to try to make quantum computers robust to noise. And then I started to work on this. And then I got kind of interested in work. I worked for a couple of years on this, and then I hired a postdoc. And the postdoc wanted to come to Los Alamos to do work on nuclear magnetic resonance, NMR, and to try to use them as a small quantum processor.
Mm-hmm.
And so I hired him with my colleague Manik Nil. And then suddenly we look at each other and says, maybe we should learn about NMR so we don't look too foolish in front of the postdoc. So we started to learn NMR together. The postdoc came, but didn't stay very long. Turned out he got a job offer at IBM and moved. But Manny and I started to do experiments. And yes, you do say, you're impressed at switching to do experimental things. NMR spectrometers are the one that we had been using then were kind of off-the-shelf things. So it's not like I had to totally build something from scratch. So I can use incredibly clever engineering of the last 50 years and kind of leapfrog this to try to build a small quantum computing processor with this. And so I thought I would do it for a few years. Like when I started to work on quantum computing, initially I thought, oh yeah, I'm going to do this for a year or two and then go back to quantum cosmology. And I plan to come back to quantum cosmology, but it hasn't come back yet. And I got kind of more and more involved with quantum computing, got more interested, and then my curiosity pushed on different things. Again, I started to do NMR for one particular reason. So we had this theory of quantum error correction, and which says that we should be able to correct these errors and make quantum computers robust. But in that theory, there are some assumptions of how the noise behave. And it seems to be physically reasonable, the assumptions, but I was not totally comfortable with them. I wanted to have an experimental demonstration. I wanted to learn more about how does the noise behave at the quantum level instead of the classical level? And will the noise be will there be some nasty things in the noise that will prevent to use that theory? And from up to now, it doesn't seem to be too nasty, but we're not there of building a fault-tolerant quantum computer yet. So, but we've made a lot of progress.
Yeah. Actually, that's a great segue to the next question. So in your capacity as someone involved in quantum computer science, and especially in your capacity as the original director of the IQC, you get asked often, when are we going to have the quantum computer? I promise I'm not going to ask you that question.
Good.
If anyone asks that in the comment, I'm not going to read it back. But if you had to think back about, Ray from the year 2000, what do you think would surprise him most about where we are right now in kind of the field of quantum information?
So I would say there's not too many things that really surprise me. It's going a little faster than what I thought. I was I was told, I was often asked the question, when are we going to have a quantum computer? And I would say 20 years, or when will there be companies that sell quantum devices? And I would say 25 years. And we are kind of now 18 years since I arrived in Waterloo. So there's 7 more years, but there are companies who are interested, like the IBM, the Googles. There are a series of startups here around Waterloo that are building devices which are being used in labs or in different situations. So this happens a little faster than what I thought. The field has expanded in many directions, which I might not have kind of predicted. So there's a lot of interest in machine learning and quantum computing. And me, I'm a skeptical until I see the good. I see this. And I bring this one as what is surprising me to me is that, well, maybe the part which is not surprising to me is the fertile imagination of scientists, of thinking about ways, different places to apply ideas of quantum information science to so many different vast fields. So that is not totally surprising to me, but the vastness surprised me. And the second one is, once these ideas comes in, sometimes I think that my colleagues are not skeptical enough. That is, they say, "Oh yeah, this can be applied to this and this." But when you go and ask them, "Okay, show me the goods or show me the proof," then there's a lot of ideas. And when you read like general public things, we hear a lot of things that are incorrect, and that surprised me that this doesn't, or some ideas gets kind of propagated in different ways. Like one of them is quantum computers will solve this travel salesman's problem. And quantum computers are not going to solve this, or nobody has proposed algorithm that solve this with a quantum computers, which people agree with. So people will say, yeah, maybe like this, but when you look at the proof, it doesn't. So there's a lot of ideas like this that gets propagated. And so to all the students of QC system there, I would say two things: be curious, but be skeptical also.
Okay. Actually, can I ask you to define one of those terms? So you mentioned the word quantum devices in there, and you distinguish that from quantum computers. What do you view as like a quantum device compared to a quantum computer, compared to something like a laser, which is a device that uses quantum physics?
So I would include a laser as a quantum device, but I would not include it as a quantum computer.
Fair.
So we think about the quantum computer as a system which has something called quantum bits, which is the quantum version of a bit. A system which we can initialize in a state which is well-defined and not too hard to reach. A system on which we can control. And we have a set of control pieces that we can do. For the technical-minded people, we can have a universal set of gates, kind of the 1-qubit gates and the 2-qubit gates. Then we know that we have universal control, which means we can do anything we want with these quantum bits. And then we have to be able to measure this, and doing all of this in a small amount of time, which is smaller than the noise time that comes in until we get to error correction. So we have a very well-defined notion of what a quantum computer is. I distinguish this from quantum devices or device which use quantum mechanics, but not necessarily for computing in a scalable way. So I should have mentioned one item which is important for computers is that they scale. That is, if you have 10 qubits, you should be able to get 20 of them, and the cost of adding the next 10 is not going up exponentially. So it goes kind of reasonable amount of resources to get your 10 more qubits. In quantum devices, I think about quantum sensors or things for quantum communication, where we are not that interested in scaling. We want to measure a specific effect. And then it turns out that quantum mechanics is very helpful to sense very feeble forces. And in fact, that's one of the main drawbacks of quantum computers. That is, they are very sensitive to noise around them. So maybe it's one of these ideas where this bug turns into a feature if you want to do it. You use the quantumness as a sensor instead of a quantum computer.
Mm-hmm. So I have one more question, and then we're going to switch to some audience questions. So audience, by all means, ask your questions in the Q&A. Mm-hmm. So you mentioned you have to be a bit careful with what you read in the news, things like the traveling salesman problem being solved on a quantum computer. You have to be discerning. So those are a couple of things that maybe give some pessimism. What's a more of a recent development that's given you some optimism for how the field's going?
The development of, I would say, a prototype of quantum computer, which with the claim that it has achieved what is called quantum supremacy, or I don't particularly like the name, but it really means that we have a device right now in the world which can do something which is faster than what one of the biggest classical computers around the world can do. So that's the experiments at Google, which showed this last fall. And although I'm skeptical about is it really quantum supremacy or not, the fact that they were able to control 50 quantum bits and do something with it this to me is the milestone that we have. So if we look at the development of quantum computation and you make a plot of the number of quantum bits as a function of time, it was kind of going up by 1 or 2 every year since 2000. So except for that experiment, everybody else has at most a dozen to maybe 20 quantum bits. But suddenly we've made a leap to 50. Now, the control is not perfect, and there's a lot of work to be done to improve this. But going from 10, 12, 15, 20 to 50 is quite an amazing thing. So there's really interesting things. There's very neat work on fundamental side. So I mentioned the kind of practical side. It's very nice work about what is called Cohn's conjecture. And it is work being done on, usually we think of the world as potentially a discrete set of spaces discretized. And although the theories that we have, like field theory, tells us that it's continuous. And there was Cohn's conjecture was, is there really a fundamental difference between a discretized system on which you take the length and you shrink it to 0 slowly, and something which is continuous? Are there observable that are intrinsic to the continuous system that cannot be seen in the discrete part? And it was solved this year, and the answer is yes. And in fact, there's a faculty at IQC, William Software, who's been kind of put some kind of building stone for this. And he's the one who's kind of taught me about it, which I find this totally fascinating. Which with this, and I'm bugging him all the time, telling him, can you have an experimental, can you turn this idea into an experiment and an experiment? And is this kind of observable, which is different? Is it robust to noise? Because when you do experiments, it's never perfect, continuous. Like we see only chunks of things. Mm-hmm. So he tells me he's working on it. So that would be neat if we could find an experiment which show this.
Yeah.
Tell us if the world is fundamentally discrete or continuous. Absolutely.
All right. Okay, so we're going to move on to some questions from the audience. So Taylor's asking, you're approaching this as a physicist, or at least you originally approached it as a physicist, but what other areas of study are involved in the physics of information? And is this highly disciplinary, and how do you reach across the aisle?
And fortunately, the institute where I work, the Institute for Quantum Computing, was really built on the idea that this field is multidisciplinary. And that part might come from the fact that I work in the national lab in the US for many years. And the approach there was often very multidisciplinary, of trying to bring people from different fields and try to make them work on different problems. And if people were keen on doing something outside their kind of own little piece of expertise, they would support you. And in fact, maybe that's part of the reason why I was successful of moving from quantum cosmology and astrophysics to do some quantum computing and experiments. They were very supportive of doing that kind of work. So indeed, if you study in a field like quantum information science, you need to be multidisciplinary. You will miss something if you're not. So I mentioned ideas of error correction, and this is not kind of native to physicists. Ideas of complexity theory, how much resources you need to compute and all of this. This is a piece of computer science. You want to build a device. So as a physicist in a lab, you can build a little device and show an effect. But if you really believe that this will be important for society in the future, you have to make it practical. And that's where the engineers are coming from. So that's kind of how things are. But what I've seen in the last 20 years is that it's even broader than this. So me, I was kind of very focused on the math, science, engineering approach. But then I got really kind of a kick out of the fact that people in the arts were interested. And I've had 2 or 3 projects which are with artists trying to do a piece either explaining something related to quantum mechanics in one way or the other. So I've done something with some musicians, and Edwin Outwater, who was the director of the Kitchener-Waterloo Symphony Orchestra. I did a program with him. I work with somebody at the Perimeter Institute, Laura Dedecker, who's an artist and kind of wanted to make a picture of what a quantum walks looks like. And so I had an incredible amount of fun. And again, my side of being incredibly curious. And so she would come to me and I would say, Laura, I can tell you about quantum mechanics, but I cannot tell you how to picture it. So this will be your job. So she would come to me and suggest ideas and say, does that make sense to you? And then I would teach her some piece of quantum mechanics. And suddenly at some point, she kind of things click and she got an idea of how to make a picture of this. So, so there's many ways that quantum information science can impact on a variety of people. And I haven't mentioned things like startup companies and kind of business people and economists and policymakers. Like the impact of quantum computers on cryptography tells us something about privacy. And then suddenly you have the world of policy and kind of, is that a good thing or not to have quantum key distribution and having quantum computer which breaks codes? And so ethics come in there. So it's incredibly vast. So I would say to people, choose something that you really like, you're good at, and kind of try to link it to quantum, and then you'll find a new area interesting to study or invest or make a fortune probably with.
Right. So actually, we talked a little bit about industry involvement there. So there's a question about that. I think this one's from Anonymous. Can you comment on how industry is approaching the quantum information processing field compared to, say, the academic approach?
Industry wants to solve problems that they have. Academics, they propose a solution to a problems that they don't have.
Can't argue with that.
Quantum computation didn't come to solve a problem from industry. It came from curiosity of people. In fact, not totally true. There was a problem about trying to build reversible classical computers. And so that was one of the hints. But most people who have worked in quantum computers in the 1980s and 90s were not that interested from the business or industry point of view, because the field was very kind of much blue sky and we didn't know exactly what the promises were. But today we do have devices. And so business people are interested at the end as the financial result of all this. This is what drives business. And we're very much in the early days. Like I would say the biggest challenge for quantum information science and technology today is find early adopters of these new technology. When you have new things, many people wait to have other people try something. Now the people who really try it, and when it works, then they get a leap ahead. So we see this, like look at the Google and the Amazon and the Facebook.
Yeah.
20 years ago, there were things that kind of people were saying, it's crazy. Who will who will put their name on a Facebook account and give all their private information, and this company is going to make a fortune out of this by advertising back to you. And so most people would have said this is a no-go. Today we know that it was an incredibly good business idea.
Yeah. No, absolutely. So I guess along those lines, what would you say to someone who, say, when people are deciding budgets for what kind of science to fund, what would you say to kind of the mindset of that science should be application based?
So when I first went to see people from the government when I was director of IQC, they would come to me with this idea of, I think it's called Pascal quadrangle or something like this, that science is divided on pure science and applied science and think short term and long term and things like this. And me, it never kind of resonated with me. I thought about this of kind of how, if I would be in the government, how I would fund science. And I would fund it through this, what I call the cycle of innovation. At the end, it all starts by curiosity. We're all curious in one way, and me as a physicist and my colleagues as physicists apply this curiosity to the world around us. And we just want to know how does it work? We want to know how does it work, because once we know how a phenomena works, we might be able to harness it and control it. Not to do what it does by itself, but maybe to kind of make it do something that we want it to do. And once you click on this, then suddenly you develop a technology which is kind of useful for many other tasks. And as you do this and you develop this new technology, it provides this new tool for scientists to go and push their curiosity in a different direction and keep this cycle going around. An example of this, I would say, is fire. 300,000 years ago, humans were able to harness fire. Took many, many years before they were able to kind of control it and harness it to be able to build tools. And when they were with it by melting metals, and when they were able to do this, then agriculture came in. And then suddenly this kind of curiosity about fire led to humans not being foragers anymore, but they could kind of do agriculture, being not in kind of very small units, but suddenly form villages that could be sustained for longer term because of the agriculture. So suddenly you see that cycle coming in. Mm-hmm. And then if you keep on that cycle, once you have tools and you have fire, then suddenly somebody will be curious about steam coming out of a cauldron. And if you put a cover on that cauldron with a hole on it, then you can make that steam kind of go in some different direction and you can harness it. And that is what happened in the industrial evolution. You can build a steam engine out of this. The steam engine allows you to build locomotives and go and get natural resources in much longer distance. And so cities, a small village became cities. And so you can go this and you can go around the cycle in. And the cycle comes in because you have piece of fundamental science, piece of trying to understand the behavior of phenomena of physics, ability of controlling them, ability of taking this control and make it do something that you want it to do, and develop technology which are useful. And as you do this, so I gave a couple of examples which made the cycle kind of go around, but there's many things where things fails, where suddenly there's a physical phenomena that we just cannot understand, or we can control it, but we can not make it do exactly what we want, or there's no application for it, or there's no application right now. So I think it's all linked, that you need to have all these pieces. And the idea of funding only one piece of that cycle might be okay for the short term, but for the long term, it's a disaster. Because suddenly you don't have this cycle coming back again. Once you have taken all the juice out of that particular technology, then you're done. You have to move to something else. So you need the curiosity, you need the fundamental science again. But the fundamental science cannot happen without having some funding from the technology that comes in and wealth of various countries. So you need all of this together. It's like a chain link. You cannot bring one piece.
So you mentioned that sometimes when we're constructing this cycle, we're trying to fit something where in our imagination it might fit in a piece of the cycle, but the world might not work out that way. So Jenna's asking, so research takes a very long time to get successful results, and there can be a lot of difficulties along the way. So how do you deal with the times where you're uncertain about your ideas, or you even find out that your ideas were wrong?
So there is never a problem of finding that your ideas are wrong. Most of my ideas get wrong, get in the wrong direction. It happens very often. I usually don't go and talk about it to everybody. I figure out that things are wrong and and then move on to the next one. I would also say that maybe the nicest piece of work that I've done are where I started with an idea and the output was completely different. So during my PhD supervisor asked me to solve a problem, and he says, try to show this. And I showed the opposite. And it took me a lot of time to convince him because he thought that I was kind of doing something wrong in the logic of all this, but it worked. When I started to work on quantum computers, I wanted to show that it would never happen. And then by poking at this, and this is where, as a scientist, you need to be honest. You look at what comes out of whatever you do. You look at the facts, you look at the equations, you look at the mathematics, and you have to be honest of what they really predict. And you have to listen to what the mathematics tells you. And then kind of you can make a conclusion. And some people try to want to have a conclusion in some different specific way at some time. You cannot do this. So it does take time, all of this. And my way, and I've been lucky in that way, I do some theory and do some experiment. So when things kind of get the stumbling block in the experiments, then I push a little bit more in theory. And that's where I think the importance of it more than one problem. It's very rare that I sit down somewhere and I try to solve one problem and I go from the idea of having that problem to solving it, having a nice solution. I poke at it a little bit. I don't know exactly how to do it. I go and look at another problem. And so I think, oh, yeah, maybe I should try this to this other place. I go and try it again. Fail again. Leave it aside, come back to it. And so I do this quite often. And right now I have students who help me doing this. And they all have different projects. And sometimes some of them kind of slow down, but some other kind of speed up. And so I mentioned two things which were important: curiosity and what was the other one that I mentioned early on? I forgot. Well, I'll add a third one, which is stamina. So to be a scientist, you have to push things. And even when you don't see the light at the end of the tunnel, you have to keep pushing. But you have to be honest. And sometimes there are problems which we don't have the tool right now to solve. And at some point you have to say, okay, this one I have to put it aside. I have to kind of do this other one. So,
Right. So we're getting a question from Angeline. So you mentioned earlier that over the summer you and your student Cheyenne have been working on a textbook for implementations of quantum computing. So out of those, there's a few different implementations that people hear about a lot. Is there any one that's your personal favorite? Any one that you think is a dark horse that not enough people are talking about? Yeah, what's your favorite?
In fact, I don't think I have a favorite. I like all of them. First, because again, I'm curious. The quantum information science allows me to go and learn about NMR, about photonics, about ion traps, about quantum dots, about superconducting devices. So I really like that part. And I try to, what our book is trying to do is to have one way of thinking, which is the quantum information science way of thinking, and then try to understand all these devices from that framework. And so once you've learned about it from nuclear magnetic resonance, can you apply the same kind of ideas in some other technology and try to differ it? So I don't have a really preferred one. Now you could ask me, maybe one will lead us to the quantum computer today. And right now it seems that superconducting qubits is a little bit ahead of ion traps. there are claims that photonics can kind of leapfrog. So I do not know what people do in industry, which is hidden, where I could make a real smart answer of saying this is the one in particular. But from what I know, from what I've seen, which will publish results, all of them have real challenges, which tells us that maybe we don't yet have the right way of building a quantum computer. Maybe we'll get over these stumbling blocks, but none of them are a slam dunk. And you mentioned earlier on in the conversation, if I go back 20 years, what I would predict. There's a case of me saying maybe in 25, 30 years, we would have decided which implementation is the best one. But I think the horses are still out of the gates, and nobody has finished yet. And suddenly somebody can be a little bit behind and catch up. And there's some really neat idea about topological quantum computers, which if we could find these topological quantum bits, then we'd be really ahead. It just seemed to be very hard to find. But again, you can have a breakthrough somewhere and get something kind of that jumps in and being very new and kind of leapfrog other places. Like there isn't enough distance between the first horse and the other ones to say there's a clear winner yet, which is really fun, right?
Yeah. We are getting very close to the hour mark, so we're going to make this the last question. So this is from Andrew. He's actually one of the students attending the Quantum Cryptography School for Young Students right now. So he's wondering what mathematics background is critical to have for quantum mechanics. But I guess more generally, do you have any advice for like high school or undergrad students who are looking to kind of get into the field? What should they be studying? What should they be learning? Any resources?
So I would say the first thing is curiosity. Be curious. That's the most important piece. Now you will say, okay, being curious, you need some tools also. So definitely a good background in math. And quantum mechanics is very much related to linear algebra. So you better learn how your matrices multiply each other and kind of how to do different operation with matrices. So if you learn this, then you have a heads up on things happening. But the field is broad enough today that there's many ways to enter this field. So if you're interested in mathematics, I would say, yes, learn about algebra, learn about operator theory and pieces that you'll learn at the university in math. But you could contribute also in chemistry. Like you could think there's work being done in trying to understand different chemical reaction, and can we have a quantum computer to try to simulate this reaction, and do we have an advantage by doing this? So we don't really know that much about this, and so they could be a part. If you're thinking from an engineering point of view, we all have to think about how do we control tons and tons of qubits together? How does the classical control that we've learned by manipulating transistors and chips that makes all the computers that we're using every day, how does this translate to the quantum world? What are the things that are similar? What are the things that are different? And how do we take care of the things which are different? So there's many possibilities, and it really depends on what your strengths are. In fact, when I hire students, the first thing they always want me to give them a project even before they arrive and start graduate, so that they can have a heads up on doing the research. And I tell them, well, first you need to build your tools, and also I need to know what is your strength and your weakness. If I give you a project that you're not interested in, then there's no point of going ahead. So find the thing that you really like, and then kind of learn about it, and then try to read a lot about quantum computation in different places and make the link. And then you'll be original.
Oh, very good to hear. Very good to hear. Well, we're just past an hour, so I think we're going to wrap things up. Thank you so much for joining us tonight, Ray. This was fantastic.
John, it was a great pleasure. I'm very happy that I was the first one in the series, and good luck for the rest. It's really
Thank
fun.
you.
And good luck to all the students, especially the QCSS students. It's a different year this year, being at home and doing this, but next year things will be different. And even if the world is different, people still hire students and graduate students. So, and we need many to kind of leap in the quantum world.
Oh, yeah, this is not a one-person show by any stretch of the imagination. All right. So thank you, everyone, tonight. Thank you for joining us. I hope you had a great time. We had a great time as well. So follow us. We hope to be doing more of these. So follow us on Twitter, Facebook, Instagram, your social media of choice, and we'll be sure to announce when the next one's going to happen. Hope you had a great time. I hope you have an amazing rest of your evening, and we'll see you at the next one. Have a great night.
Take care. Good evening.